Okay, so in the last class we have read about, we have started main memory. I think I have not yet put it in Google Classroom. Let me upload it. So any doubt in the last class, main memory? We have read about two types of memory: logical memory, physical memory, swapping. Okay, and we have seen a base register and there is a register. Base register will store the starting address of this program, and limit register will tell you up to what size that program is taking space, from the base to up to what size. Then we have seen static address binding, dynamic address binding. We have also seen absolute addressing, relocatable addressing. Absolute addressing means program will always map to that particular address whenever it will be executed. But we never use those type of code. We use relocatable code where operating system can put the whenever you double click one program, it can put the program in anywhere in the main memory, and also it can change the address of the program during execution. Okay, that's why it is called a relocatable address. Okay, loading time, you might be having one address. After some time the operating system might change the address of that program to somewhere else. So whenever it will be changed, the base address, the base register has to be changed. Okay. We have seen logical versus physical address space. Can anybody tell me what is the difference? Logical versus physical. Unmute and tell. And I've told you it is very important. What is logical address space or the virtual address space, and what is physical address space? Can anyone tell me? Anyone? Ishita? Ishita? Smile win. Anisha?
So logical address space is basically when the address is in, and physical when the address is in the memory or the
Address is inside the CPU.
no, like you add the address from CPU. I mean, you add the address from RAM
Hmm.
uh, with the address in CPU.
Why to add? Anyone else? Abhijit? Kamesh is telling physical address location in memory unit. Is CPU during its execution. Yes. Logical address is generated by CPU. I am not asking about what is logical address, what is physical address. I am telling about where these addresses are located. Logical address space and physical address space. Obviously, you know what is physical address space. Physical address space means your space inside your RAM. But what is logical address space? If you are having a 2 to the power 32 bit machine, what is the size of logical address space? Yes, Subramaniam is saying logical is from user point of view, physical is how it is in RAM. Yes, that is true. Logical address is not given by CPU. When you execute the program, that inside that program logical address is mentioned. That's why CPU generates logical address. It's a reference to access the physical memory location by CPU. Yes, but where this logical address space exists? Can anybody tell me? Physical address space like it is existing in RAM. Where is this logical address space? If I have a 32-bit machine, what will be the size of logical address space? If you are given a 32-bit address, 32-bit bits, how many different types of combination you can generate? 2 to the power 32, right? Yes. So if you can generate 2 to the power 32 from a 32-bit address, that means what? The space you are having is 2 to the power 32. Okay. So if you are having a 32-bit machine, then you can generate 2 to the power 32 number of different combinations, and you can represent each combination as one address for each byte. Okay. So at the end you can able to identify 2 to the power 32 number of bytes. Okay. And last time also I have told you, if you are representing 2 to the power 32 bytes in GB, how much GB it is? 4 GB. Okay. But if you are having a 64-bit system, then you are having 2 to the power 64 different combination of addresses. Okay. So that is a logical space, 2 to the power 64. Okay. I think you have already completed what is that microprocessor. Have you done the lab? Have you done the lab like 8085 or something? Have you done any simulation regarding written any code in assembly language? Yeah, 8086 or 8085, anyone? Okay. So for each code, are you having one address for each line? For each line in assembly language, are you having one line, one address? Okay. Okay. So now you can understand that each instruction is present inside one address. Okay. So again, it depends upon instruction how much space it will. Okay. 8086 is how many bit processor? 8086. How many bit processor? 16 bit. Okay. And 8085? 8 bit. Okay. So whenever you have written the first instruction, what is the starting address of the processor? Means whenever you have written the first instruction, what is the address? If you remember, what is the starting address of the first line, first instruction? 0000. Nice. So 0000 means it is the starting address. And how many different types of combination you can generate? For 8 bit, you can able to generate 2 to the power 8, right? So at the end you will get 1111 or something like that in hexadecimal. This numbers that you are telling, it is in hexadecimal, I think. At the end there will be one H, 000H. Okay. So that is in hexadecimal. That means what? At the end you will get 1111. So that means what? You are having a all types of combinations starting from 0 to 1. Okay, so it depends upon how many bits are there inside that, means how many bit processor is that. Okay, so if you are writing in a 32-bit machine, you are having 2 to the power 32 number of different combinations starting from 000 32-bit to 1111 32-bit. Okay, so that is your logical address space. Okay, and obviously no programmer writes that many number of lines. Okay, logically we have that much amount of space, but normally user writes around 100 lines of code, 1000 lines of code. Nobody will write 1 billion number of codes, right? 1 billion number of instructions inside the program. Code means I am converting into assembly level language and calculate. Okay, so if you will not write that many number of lines of code, and also this logical space is very huge than the physical address. Okay, so there we also seen that there has to be some mapping between the logical address and the physical address, because like you have already told that first instruction is 0000. So obviously all the program will start with 0000, and if you are taking 0000 as the starting address for all the program, whenever all the program will be executed, all will be mapped to the starting address of the RAM and all will be overwritten. Okay, so that's why what this 0000 is not the physical address, it is just the logical address you have given or the program has generated. You are keep on writing one instruction, the address will be keep on incrementing. Okay, so I think the first address is 4 zeros. In the second address, I think you will be having 0003 as the next instruction. Am I right? The next instruction address is 0003 or anything else. If you remember the second instruction address. Okay, so whatever it may be, it will be automatically incremented. The address will be automatically incremented and you have to keep on writing the instructions. Okay, so what will happen, whatever instruction addresses are generated by you, all are in logical address space. That's why it is called is the set of all logical address generated by a program. Okay, logical address space is generated by the program, that means it is the logical space. In logical space, I think also you have implemented some function or some jump instruction from one address space to another address space in assembly level language in microprocessor. Okay, so in that case you have given some address, jump to this address, suppose 1000 or something, and that again that address is also logical address, right? So whenever you have given any address while writing the program, all the addresses are logical address. Okay, but whenever you will go into a physical address space, there your program may be loaded into any physical address space. That means any starting address can be anything. It can start at 1000 byte, or it can start from 10,000 byte, or it can start from 1500 byte. So we don't know where operating system will keep our program. Now our problem is how to map this logical address to physical address space. Okay, so for that we are having a table which will tell this, if this is the logical address space, go to this physical address. Okay, so that's why MMU came, memory management unit. Okay, it is a hardware device present inside the processor. When what it will do, it will get the input as the logical address and it will provide the real address. Okay, so the user program deals with logical address and never sees the real physical address. In the execution time, logical address will be converted into physical address by the memory management unit. Okay, so in this case base register is also called relocation register, because the base register will be having the initial starting address of that program. Okay, And sometimes we are having many number of relocation register, 4 to 8 number of register, depends upon the processor. Okay. So what is the use of that? It will convert the logical address to physical address. Okay. So how it will convert? It will take the logical address, then you have the base register. Okay. You add it to that, you will get the exact memory location which CPU wants. Okay. You know the initial address of the program. CPU is demanding 346. That does not mean 346 of the RAM. It means after 1400 get me the 346 number of 346 address. So you have to add this plus this and you will get the exact address in the memory. Okay. Then we know what is static linking, what is dynamic linking. Dynamic linking we are already always using, because we have to link the logical address to physical address while running the program. Okay. We have also seen swapping when our physical memory will be overloaded. That means it is full. You have to get some of the program out from the memory and put it in the backing store. Okay. Backing store means it is a hard disk. In our case, it is hard disk or SSD, whatever it may be, whatever you are using in your operating system is installed on. If you have two hard disks, wherever is operating system is installed, that will be act as a backing store. Okay. And I have already shown you those 2-3 files in your C program, in your C drive. So whenever memory will be full, some program will be goes out of that memory and stored in hard disk. Whenever it is needed, it will come back into the memory again. Okay, so that's what it is called: roll out, roll in, or swap out, swap in operation. Okay, swap out means swap out from the memory to hard disk. Swap in means from hard disk to memory. Okay, so this is swap out operation from memory. You are going out to hard disk. Swap in, process 2 is swapping in into the memory. Okay, so this is what keeps on happening if you are having a low memory PC. Okay, PC or laptop or mobile phone, whatever you have. If you are having a low RAM, then this process is keep on happening, and due to this process, hard disk is very slow. Due to this swap in and swap out process, you will feel that your PC is slow or your mobile phone is slow, because your RAM is full and this is keep on happening. Okay, this will be swapped out. After 1 second, this will be swapped in, and this will be swapped out. Then after 1 second, you will switch to this app. This will be again swapped in. This will be swapped out. So this will keep on happening. So that's why a bigger RAM is better. That's the main thing. Okay, why they call bigger RAM is better? Because of to avoid this swap in and swap out, we want to keep all the processes in the RAM. Whichever processes we are using, multiple processes we are using at a time, we want to keep a bigger RAM so that this swap in and swap out process should not happen. Okay. If this will happen, that means you have to access the hard disk, and hard disk is very slow. That's why you have to keep on upgrading your RAM space. Okay. And context switch time will also include the swapping time. Suppose one program is needed by CPU and that program is not there inside the memory, then what will happen? And also memory is full, then you cannot just bring the CPU demanded program into the memory. Why? Because memory is already full. So you have to create a space for that new program. So that's why you have to send some process out from the main memory to hard disk, and then you will load the new program. So that is swap out operation. So swap out operation, you will be timing will also be included in context switch. Okay. So whenever any switching will happen, and if that program is not there in memory, then you have to create a space for that program by removing one program from the main memory to hard disk, and then bringing the required program by the CPU to memory. Then it will take lots of time in swapping. Okay, plus context switch time. Okay, so that's why It is very slow if you are having a smaller RAM. Okay. One more constraint in swapping is that if one program is waiting for IO, you cannot swap out that process. Okay, this you have to remember is that whenever you are having a program that is waiting for IO operation, you cannot swap out. And standard swapping is not used in operating system currently. There are some variants of swapping that is used. Then we will see two different types of allocation of main memory. One is contiguous allocation, one is non-contiguous allocation. Contiguous means, you know, it is the serial allocation. One is allocated, after that next is allocated, next program is allocated, next program is allocated serially. Okay, it's like an array. So main memory must support both OS and user process. You know, operating system, some part of the operating system is always present inside the main memory. So main memory has to contain the operating system required files, processes, and also the user process. Because main memory is limited resource, we must allocate it efficiently. Okay, RAM is very less space, so you have to allocate it efficiently. So first method is contiguous allocation. This is the very early method and nobody is using this contiguous allocation currently, but still we will see what is this. So main memory usually partitioned into two parts. Okay, one is for operating system part, another one is for user processes. Okay, so these operating system files and interrupts are present in low memory space. Low memory space means addresses starting with 000. Okay, address starting with 0, that will keep the operating system files or processes and interrupt vector. Can anybody remember and tell me what is this interrupt vector? What is the use? You put the answer in comment. Okay, user process then held in higher memory. User processes, whatever you double click, whatever process you are creating will be after the operating system. After the operating system processes are over, the space is allocated, then user processes will come. And each process contained in single contiguous section of memory. So each process will be given some part in the memory. Then the next process will be allocated, then the next process will be allocated, and they will be allocated serially, contiguously. Okay. Relocation registers. Interrupt vectors means helps in calling ISR when interrupt occurs. Now, memory location of ISR. But what is the vector? Vector thing. Interrupt vector means it contains lots of interrupts. When lots of interrupts are happening at the same time, then interrupt vector will decide which interrupt has the highest priority and put them in the queue. Yes, prioritize the interrupts. Okay, so don't forget those things. Those things will come in either GATE exam if you are preparing for GATE exam, or maybe in interview. Okay, so those are important things. Computer organization and operating system, these are very much related. Okay, so relocation register used to protect user process from each other. Okay, relocation register, we know it is the base register. Base register will protect the each process so that one process cannot get the code from other process. Okay, suppose one virus program came and you are executing the virus program, the virus program cannot access the other program. So that protection has to be given, and you know already how to give that protection using base register and limit register. This we have already seen. Okay, so if one program is present, starting address is this, the ending address is this, and it is generating some address which is out of that limit, that means what we will do, we have to trap it. That means we have to end that process. That means it cannot able to access any illegal location. Okay, so multiple partition allocations are there. That means process 5, process 8, and you can see all are allocated one after the another. But what is the problem in this contiguous allocation? If one process is over, suppose process 8 is completed and it will leave the it will leave the RAM, and there will be a hole will be created here. Okay, then after that what happened, some process 9 came, it is located here, then after some time process 10 came. So now if process 11 will come, and it will be having a size bigger than this free size, then process 11 cannot fit into this memory. Okay, so that is a problem. Suppose some memory is also here, some memory is also here. If we combine this memory plus this memory, then we can allocate the process number 11. But process number 11 has to present contiguously. So that's why process number 11 cannot be able to, we cannot allocate that process number 11 here plus here. Okay, so suppose some memory is also present here. Okay, so let's take some memory is also present here. Process number 11 requires this memory plus this memory, then it will be allocated. But because it is contiguous allocation, we are reading about contiguous allocation. Without contiguous allocation, we cannot able to put process number 11, because half part will be here, half part will be here. That is not allowed. Okay, so that means what? This space is wasted, this space is wasted, and process number 11 cannot come to the memory, and it can never start. Either you have to remove some process from the RAM and put 11, even if the space is present. Okay, you got the problem in this case. Even if RAM is having some space, but they are not consecutive to each other, so we cannot able to put process number 11, which require this plus this number of space. Suppose this is 10 bytes, this is 10 bytes, 20 bytes. Process number 11 is 20 bytes. So we cannot make it half put in this space, half we will put in this space, because it is contiguous allocation. We cannot able to do that. So that is the problem in contiguous allocation. So that's why nobody is using that. So we are getting holes. When holes will be there, then what will happen? Due to this hole is wasted. Okay, this hole is wasted. It is a block of available memory which is not allocated to any process. That is called a hole. Okay, and you can see these are variable partition. That means the size of the processes are different. Obviously all the process will have different sizes, because all the program are not of same size. Okay, when a process arrives, it is allocated memory from a hole large enough to accommodate it. Whenever a new process will come, it will put inside a hole which is bigger than the process is asking whatever memory. The hole should be bigger than that. Okay, so for that there are 3 types of algorithms are there to put which process to be put in which hole. Okay, so the first one is fast fit. What is this? Allocate the fast hole that is big enough. Suppose one 5 KB, suppose one 5 KB program will come, and in the RAM, if there is a this memory is free. Okay, and there are other memory spaces are also free. Okay, other memory spaces are also free, and this is allocated already to some other program. This requires 5 KB of space. This is 100 KB. Okay, this space is 100 KB. So according to fast fit algorithm, 5 KB is less than 100 KB. So first it will check this space, it is allocated, so we cannot allocate anything. This space is free, it is 100 KB, it will put its code here. Okay, understood? Whenever you got the first free space which is bigger than 5 KB, we will allocate there. Okay, but what about these spaces? Other spaces, they are of 5 KB each, suppose. Okay, they are of 5 KB each, and now we have allocated a 5 KB process inside a 100 KB space. Okay, so total 95 KB is still left inside this hole. So there will be new hole created of 5 KB, and rest is 95 KB left. Okay, so the first bit will take starting, it will scan from start to end, and it will see if any space bigger than 5 KB available, it will put the code there. Best fit means what? Allocate the smallest hole that is big enough. Okay, so what is the smallest hole in this case? The 5 KB can go into 5 KB space, yes. So it will not put in here, even if 100 KB is there, but it will not put it here, because if you put 5 KB inside 100 KB, there will be a hole of 95 KB. Okay, so that's why what it will see the perfect match for this 5 KB. So it will scan entirely and it will put somewhere here, because it is 5 KB, so it can accommodate 5 KB program. Okay, so that is called the best fit. Wherever it will see the best fit size of this program and free space, it will put there. Worst fit means what? It allocates the largest hole. Okay, so it allocates the largest hole means what? Suppose there is a big hole here and it is of 1 MB. Okay, and this 5 KB will be coming here and it will check everything and it will see the biggest hole is this one. So this 5 KB will be put here. So 5 KB space is gone. Rest will be another hole. Okay, so that is the worst fit. So there are three methods: first fit, best fit, worst fit. Any doubt in these three? First fit is wherever you see the space, put your program. Best fit is wherever your program and the space matches, then you will put it. And worst fit means put it in your biggest free area. Okay, done. So due to that, we are having two problems. Due to this allocation, we are having two problems. So let's see what is the problem. Problem is, suppose you have a space this much and one program came and has taken up to this much area. It is filled. Okay, this much area is filled. Now rest amount is this part. Okay, rest amount is this part. So this is called the internal fragmentation. This part is called internal fragmentation. Okay, internal fragmentation. What is this? Allocated memory may be slightly larger than requested memory. So requested is this much memory, but allocated is this much big amount. So some part of that will be wasted. So this is called the internal fragmentation. This part is wasted because this part is not needed for this program. Only this much amount is enough. Okay, so what will happen here? Allocated memory, whatever memory is allocated, may be slightly bigger than the requested memory. This size difference in memory internal to a partition but not being used. It is internal to this partition is this much big and we have allocated this part. So this part is called the internal fragmentation part. Okay, now what is external fragmentation? External fragmentation means total memory space exists to satisfy a request, but it is not contiguous. I have already told you this problem. The problem is the space is here, but it is not contiguous. So we cannot put the process number 11 here. So this is called external fragmentation. Due to external fragmentation, we cannot able to allocate the process number 11 because they are not contiguous. Okay, even if 20 KB is available, we cannot able to put the 20 KB process. Okay, this is called the external fragmentation due to non-contiguous problem. Okay, so the problem you know now. So what is the solution? Obviously solution is don't use contiguous memory location, use non-contiguous memory location. Okay, so we will see what is contiguous and what is non-contiguous, how to go about it. But before that, there is a small solution to this problem, these two problems. What is the solution? Solution is compaction. Okay, so what is compaction? Compaction means the memory management unit will do something, and after doing this compaction operation, all the free memory space will be together and all the allocated memory will be together. That means what will happen after the compaction process, this process 2 will go here and all the free memory space will be combined into one big chunk. Then after that, process number 11 can be put inside this big available memory. Understood? we will shift this process to the top because it is free. So what will happen? All the non-allocated space will be one side, all allocated space will be on other side. That is called the compaction. Okay, but there is some limitation to that, because all the processes which are waiting for IO, we cannot able to shift them. We already know this. If any process is waiting for IO operation, we cannot able to shift its starting address. That means we cannot able to change the base register of that program. Okay, and compaction is possible only if relocation is dynamic. It is only possible if it is the binding is not static, it is dynamic. Okay, so then there is a next type of memory allocation, which is called segmentation. Okay, what is segmentation? Segmentation means, like user views the program, segmentation also will work like that. That means user views a program like a main program, a function call, a procedure or a function call or a method, some objects. Program consists of all these things, right? Stack, symbol table, array, common block, local variable, global variable, all these things. Okay, so these are one segment. These are all called logical unit of a program. Okay, so like that we will also see it like that. Okay, this is the user view of a program. A user view means the program is divided into a main program, a subroutine, a stack, symbol table, a SVRT function, any function. Okay, so these are present in logical address like this. Okay, these are the logical view or viewed by the programmer. Okay, the programmer sees its program like this. So if this is the logical view of the program, anyway we have to store it in the main memory or the physical memory, right? So how to implement this? Just put this one segment in somewhere inside here, put the second segment somewhere here, put the third segment somewhere anywhere in the main memory, put the fourth segment anywhere. So now you can see that it is non-contiguous allocation. Okay, that means one program is not sequential. Also two free spaces are there, and these are non-contiguous allocation. Okay, it is not like one will be there, two will be there, three, four. It should not be contiguous. It is non-contiguous memory allocation. Okay, but what will happen? We need a table to remember that one goes here, segment number 2 goes here, segment number 3 goes here. So we have to remember where it is allocated, which segment is allocated where. These are the segments from a single program. Okay, I am not talking about different programs. I am talking about only one program. And again, inside one program there are other segments are there, and based on these segments they are allocated different memory space in main memory, and they are also non-contiguous. So if possible, program number 2 can put its segment number 1 here. Okay, so this is program number 2 segment, this is program number 2 segment number 2. Like that also we can able to put. So this is non-contiguous memory allocation. This is how you have to do it. Okay, so to support that segmentation architecture, we have to divide our address into two parts. One is segment number, one is offset. Okay, so what is segment number? Segment number means these numbers. Segment number 1, segment number 2, segment number 3, segment number 4. Okay, so whatever the address here, each instruction will have address. So address is now divided into two parts. One part will tell what is the segment number, and another part will tell what is the offset we are going to use. Okay, then there will be a segment table that I have told for mapping into the physical address. Okay, from logical address space to physical address space, we have to map using the segment table. And we will have a base and the limit register like the previous. Base will tell you the starting address of the of that segment. Limit will tell you what is the size of that segment. Okay, then there are two registers we will be using in this case. One is segment table base register, which will point to the segment table location in main memory. wherever is this segment table in the main memory, that starting address will be present inside this register, because whenever we want to execute that program, we have to check where is that program is loaded in the main memory. How to know? From the segment table. How to know the segment table starting address? It will be here. Okay, base register. Segment table length register will indicate how many number of segments this program is using. This program is using either one segment or multiple segments. Okay, so if segment number S is less than STLR, then only we can able to run that program. Okay, suppose this program is asking for segment number 5, but there is no segment number 5. Okay, so at that time what we will do, we have to terminate that process. Okay, because there are only 4 segments are there, and also it is mentioned in segment table length register that how many number of segments are there in this program, 4. But if it is asking 5, then this is violated and we have to stop that process. Okay, so that's why we have to keep track of the starting address of the segment table, and also we have to keep track how many number of segments are there per program. So that's why we have to check for the protection. Okay, so in this case, protection is given by a valid bit. So with each entry in segment table associate with a valid bit, that means 0 means illegal, 1 means valid. Okay, read, write, execute privilege also we have to see which part of the memory can be read, which part of the memory can be write and execute. These are all coming under protection. Okay, protection bit associated with segments. Code sharing occurs at segment level. Now, what is the benefit of segmentation is that, suppose this segment number 2 is for SQRT program. Okay, suppose segment number 2 is SQRT program. SQRT program is used by this process, and one more process is also there which will share the code of this process. That means what? The SQRT program, the SQRT code is also needed by this process number 2. So at that time what will happen? This code will be shared by this process and this process. Okay, so that is the benefit of segmentation, is that the code sharing is easy. Because if one program need this code, another program also need that code. So 2 times the same program will same code will not be loaded, it will just be shared. Okay, so what will happen for the segment table of this process? The segment table of this process, 1 will be somewhere pointing to some process, 2 will be pointing to this. Okay, so program number 1 also segment number 2 is here, program number 2 also segment number 2 is here. So this code will be shared among these 2 processes. Okay, so that is the benefit of segmentation. Since segments vary in length, memory allocation is a dynamic storage allocation problem. Because the segment size are different, you have seen the segment lengths are different. Memory allocation is a dynamic storage allocation problem, because again you have to dynamically store all the programs. Okay, we have already told that we are not using static allocation, we are only using dynamic allocation. Okay, so one example is here. You can see CPU will generate the logical address. Logical address will be divided into 2 parts. One is called segment number, this is the segment number, and D is called the displacement or offset. Okay, segment number will go into the segment table. Inside the segment table you will find the base address of that segment. So suppose segment number this is being used, this is being requested by the CPU, so this segment number will come here. Okay, and this offset will be checked with the limit, that this limit will come from here. It will check the limit that, suppose this is limit is 100, and you are checking that this segment limit is less than 100 or not. Okay, okay, so we are checking the limit here. Okay, this part is for checking the limit. If both are yes, this is yes, and you got the base address, so combining both we can identify a byte inside this segment. Okay, this is how it works. So let's take one example. Suppose segment number this segment number 0, 1 and 2, there are 3 segments inside this program number 1, and segment number 0 is from 0 to 499. Segment number 2 is a SUB1 program. This is from 0 to 199 and 0 to 19. Okay, so this is the segment mapping table or segment table, where you can see for process number 1, segment number 0 is starting with address 3000. Okay, 3000, that is the starting address, and you have seen that its size is 500. Why? Because 0 to 499 it is 500, limit is 500. Okay, access is executable, that means you can execute. Sometimes what will happen, this part, this code part or this code part may be present in hard disk. That time what will happen, we cannot able to execute that because it is in hard disk, not in RAM. So you have to first bring it to RAM, put the base value and limit value, then only we can make it executable. Okay, so you can see the sub1 program is loaded where 4000, so we have to write 4000 in base address section, and obviously limit is 200, so we have to put limit as 200. Okay, so this is a simple segment map table. There are multiple other things like valid bit, all those things are protection bits are there. Okay, so we are just looking at a simple base table. Okay, so whenever your processor will generate one logical memory, the memory will be the memory address will be divided into 2 parts, because this memory address is written in bits. Okay, number of bits. So some bits will be used for segment number, some bit will be used for displacement or for checking this limit. Okay, segment number will go here for checking what is the base address. Limit will be checked with this displacement will be checked with the limit. If it is less, very good, get the starting address and it is combined with base address plus the limit, and we can able to access that section in the main memory. So this is how your segmentation is done. Okay, any doubt in this case? Any doubt in segmentation? Okay, now there is another what is that, there is some problem in segmentation, that's why paging came. Okay, so what is the problem in segmentation? Problem in segmentation is that these segments are of varying length, that's why dynamic storage allocation problem will occur. Okay, because the segments are of varying length, then 2 types of problem will come. One is internal fragmentation, another one is external fragmentation. Either you allocate them contiguously or non-contiguously, these 2 problems will be there. Okay, so can anybody tell me, in segmentation internal and external fragmentation will both will be there, only one will be there? In segmentation we will be having both internal and external fragmentation, or only one? Which one, Kamesh? Internal or external? Only external. Why only external? Let's go to that photo and let's analyze here. Okay, here suppose this part is free, right? And for process number 2, one small segment will come here and we can put it here. That size is smaller, so we can only take this part. So obviously this part goes for internal fragmentation, right? another process will come with a smaller size, and we will put it in this segment, this free segment. So obviously some part of the memory will be left, so that went for internal fragmentation. So internal fragmentation will be there. What about external fragmentation? If one big segment will come, this much big segment, and we want to put it by joining this and this and this, not possible, right? If this big segment of this process number 2 requires this, this and this, but all these three are in three different places, these two we can able to combine into one, but this is somewhere else, because this and this spaces are already allocated for process number 1. Then we will be having external fragmentation, because these spaces are not in contiguous. Okay, so both will be there, internal and external, both fragmentation will be there. So that is called the problem of dynamic storage allocation problem due to varying length. Okay, so what we understood is, if our size of the allocation will be of varying size, then we will be having internal and external fragmentation, and that is a very much wastage of space, because we don't want to waste these spaces. Okay, so what will happen now? What will happen? We will go for a final type of allocation scheme, which is called paging, which every operating system uses. Okay, so what is the concept? Concept is make all segment fixed. All the segment size will be fixed size. Okay, all the segment size will look as if all are same. Okay, all segment size will be of same size. Mostly it is 4 KB. Mostly it is 4 KB for all the operating system, but in many operating system they might be supporting more than 4 KB. In Windows, the minimum is 4 KB. The minimum page size is 4 KB. Okay, what is page I will tell you. Okay, don't worry, it is just a space. Okay, so all the spaces are of now 4 KB. That means in main memory, if you see the main memory, all the spaces will be divided into same size. Okay, all are of same size. Okay, so what is the benefit now? So if all are of same size and program is also divided into same size, okay, so this is also 4 KB, this is also 4 KB, so exactly it will fit. Okay, exactly we can allocate this to these 4 KB segments. Okay, so in this case, what you understood from paging, can anybody tell me if internal or external fragmentation will be present in this case? The program is also divided into 4 KB. The memory RAM is also divided into 4 KB. So which type of problem will be there, internal or external fragmentation? Or no problem? Internal fragmentation will be there. How? Obviously external fragmentation will not be there, because we can now allocate any 4 KB space to any 4 KB space. Okay, because the sizes are same. Only internal fragmentation will be there. Sir, over, sir. Sit, sir. Sit. So only internal fragmentation will be there if there is a 3 KB segment from the program. Okay, so if there is any 3 KB segment, if it will be allocated to a 4 KB segment, then 1 KB is wasted. That is called the internal fragmentation. So as Jesse said, it will be having internal fragmentation, but there is no external fragmentation now. Okay, so in the next class we will be starting the paging part, and I have already uploaded this PPT. You can go through it. Okay, thank you.